Today we go back to more foundational stuff, and now we're going to talk about states and measurements of composite systems, focusing on two qubits. But the things that I want to highlight here, they are not special for two qubits; they are more general. But we are focusing on two qubits because we are going to use two qubits for applications next class. So next class, Wednesday, we go back to applications. So we're going to talk about protocols using entanglement using two qubits. So today we're going to understand states and measurements in two qubits and define what entanglement is. Okay. Again, feel free to stop me anytime and ask questions. Okay. Okay. Again, references. You can still follow this book. It's section 2.14 in chapter 8. And on Newton Schwann, there is the more traditional quantum information computation reference, bibliography. This is section 2.2.8. Okay. Again, this is really important. This is the basis for everything that comes next. So it's really important that you understand everything I'm talking about. So if you have any questions, any doubts, please stop. Okay, so last week we focused on one qubit, understanding state, measurements, probabilities, final states after measurement, and applications to cryptography. Now this week we focus on two qubits. Okay, so if we remember what happens with a bit, a classical bit is a variable that can assume two values, 0 and 1. And a qubit, by contrast, has two extremal states that are the basis, an orthonormal basis for the Hilbert space of the system, but the states are, in general, superpositions of these two states. So we start with two orthonormal vectors into two, but the states can be superpositions with mathematically translate into linear combinations of these two vectors, remembering that we have the normalization conditions for alpha and beta. Okay, so we talked about this a lot. Now, if we think about something similar, but for two bits, two classical bits will have four possible values. We can vary the first and the second bit independently, so we'll have four possible states. And now if we think about the same thing, two qubits will have four extremal states that will be an orthonormal basis for the Hilbert space. So here we have a basis with four elements, so we are thinking about C4. And the general state is a superposition of these states, so we will have something similar to this here. Okay, so just by mimicking what we have done for one qubit, we can construct the Hilbert space of two qubits. Okay, but it happens that there's more mathematical structure here than just mimicking what we have with one qubit. So that's the point of the lecture today. Talk about the mathematical structure behind this and also the measurements that we can apply that we are talking about later. Okay, so now we'll dive into the mathematics of this description of the state space of two qubits. And for that, we include a postulate in our list of postulates that we have listed in the first lecture. But now we will include a postulate to say what is the Hilbert space of a composite system. So I have system A we have system 1 with Hilbert space H1, and we have system 2 with Hilbert space H2. Now I need to construct a Hilbert space to describe the composite system when I'm describing system 1 and 2 jointly, which happens a lot in physics. So what this postulate says is that the composite system is what we call the tensor product of H1 and H2. So this Hilbert space is what in linear algebra we call the tensor product of these two states. So these two states. Okay, so as you can imagine, we already knew that 2 qubits would be something like C4. The space of 1 qubit, the state space of 1 qubit, the Hilbert space of 1 qubit is C2. So if we make the tensor product of 2 copies of C2, 2 qubits, where we will have something that is isomorphic to C4. Okay, let's understand why. So we start with 2 complex vector spaces, V and W, and we get one element of V and another element of W. And now we create a new element that is the tensor product of them. In a minute, we're going to see what is the matrix representation of this tensor product. And this new element of this new Hilbert space is what we call the tensor product of V and W. Okay? Now we're going to add some properties. We're going to impose some properties to the operation of taking the tensor product, and it's basically that it's linear in each entry. And the tensor product of these 2 vector spaces that we'll denote this way is just the vector space generated when we take all linear combinations of vectors of this type. Okay? And here are the properties that we are posting on the tensor product. So it's basically linearity on each entry. So it's linear in V and also linear in W. Okay. With this linearity constraints, it's not difficult to show that if we take a basis for V and a basis for W, the set that we generate by taking the tensor product of each element of this set with each element of this set is going to be a basis for the tensor product of V and W. Okay? So as you're going to see here, if I have M vectors here and N vectors here, in this set, I will have M times N vectors. Okay? So the dimension of this guy will be the product of the individual dimensions of V and W when we are dealing with finite dimensional vector space. Okay? Okay, so if we are using 0 and 1 as a basis for C2, the basis for the tensor product of 2 copies of C2 are going to be this one. Okay. And now we're going to simplify this a bit so we don't have to write this big symbol every time we're talking about this tensor product. So we are going to use this notation. So whenever you see the 5 notation, generally it's huge thing here. Okay. Sometimes we have to be careful. Simplifying may cause us to have trouble with notation or understand it correctly. But whenever you see this kind of notation, it means the tensor product of these 2 vectors. Okay. So going back to the 2 qubit system, remember that we started with something like this, mimicking what we had for 1 qubit. Start with 2 classical bits, and we promote the classical states to an orthonormal basis. And here we have something similar, but with the structure behind it. Now these represent the tensor product of two vectors. Okay. So this is, I should have another, well, I should have another slide here. Disappeared, I don't know why, but let me write here. So it is important to notice that each of the um, each of these symbols here, they represent a tensor product. So this is tensor 0, 0, tensor 1, 1, tensor 0, 1, tensor 1. Okay. Okay. Matrix, and this is the basis. So remember that when we have a general state, will be a linear combination of vectors. So um, state of two qubits will be something like this. With the normalization function. Okay. My memory is horrible. Uh, Unfortunately, we do not have a beautiful representation for two qubits as we have the loss sphere for one qubit. So we don't have this relation, one-to-one relation. Uh, States of two qubits that point in a beautiful point, a beautiful shape are three. So we have to work with these vectors directly. Questions so far? Okay. So I'm talking about the vector spaces, and in general, we can always keep the discussion abstract and just talk about elements in a vector space. That's it. But when we are actually dealing with specific systems, it's nice to have a matrix representation for them. Okay, so since we are still talking about finite dimensional systems, we can talk about matrices, especially for two qubits. This will be 4x4 matrices. And the tensor product means an operation with the matrices. Let it be vectors or square matrices, okay? So what we have is that the matrix representation of the tensor product. Here I'm using matrices, but it could be vectors as well. Okay. You can compute the entries of the matrix representation of the tensor product using the entries of each of the matrices. So what we are going to do is to keep the matrix B and multiply it by the entries of A and use this as a block inside the matrix. So we start with two 2x2 matrices and end with a 4x4 matrix. I use matrix here. I don't know why. This is going to be important later. But for now, we are using vectors. So let me just show you what this operation with the vectors will be. Okay. Um, Here we're talking about two states, Taiwan, side two. So I imagine that Taiwan is the state of 2-bit 1, and type 1 is the state of 2-bit 1, and type 2 is the state of 2-bit 2. And Taiwan has a representation in 1, bit 2, in type 2, 1, 2 entry of each vector. So this guy here is the tensor product of these two matrices. A1 divided by 2, now divided by 1 as blocks of this field. So this is going to give us A1, 1, A1, 2, 2, 1, A2, 2. Okay, so this is the matrix representation of this tensor product with respect to a special choice of bases, remembering that every time we relate elements of a vector space with matrices, this implies a choice of basis. So there is a choice of basis here to write this coefficient. There is a choice of basis here to write this coefficient. And here, this carries out to a choice of basis here. Which basis? The tensor product of these bases with these bases. Okay? So if we have our standard basis, well, if we do all of the tensor products, 0, 3, 1, 1, so 1, 1, 1, 1, 1, 2, 1, 1, and the other products similarly are going to give us the other vectors in the canonical way. As you can check. Okay. So this matrix representation is what we use when we actually make calculation with these things. So it's important to remember that we always can connect the matrix representation of the individual qubits with the matrix representation of the joint system. Always remembering that there is a choice of basis when we do this connection. Okay. Homework, compute. So we will also apply for homework. Compute relations for the trace of matrices when they are square for you to compute, right? Also, you can define a scalar product of the tensor product by computing the scalar product of the first two entries here and the second entry. And this only defines the tensor product for elements of the tensor product that can be written this way, which will see in a minute that's not the only possibility. So we extend to other elements. Of the product by layout. So we build on the scalar product of the individual systems to build the tensor product, the scalar product in the tensor product. Okay. When we're talking about matrix representation, it's going to carry out naturally as we expect. So if we just take the matrix representation of these vectors, we can put the visual tensor product on them. Okay. Okay. Now we come to one of the most important definitions of our course, which is the definition of the composable vectors. And so we are all the time talking about tensor products of this type. Okay. So we were focusing on the mathematics side of the thing, trying to understand the object, the vector space, but we are doing that with something in mind. So what we have in mind, we want to represent the state of two qubits. So what is the physical interpretation? So we imagine that we have two physics. What we have two. So there are two labs far apart from each other. They not communicate. They are not aware of the existence of each other. Each of them prepares a qubit in a case. Lab 1 prepared one, two pairs. That what is the representation for the state of that joint system? Two independent qubits. There is no correlation between them. They never interact. They were independently prepared. The first one was state 1, the second one is state W. So the joint system will be described by this tensor product. Okay? Okay. But we can apply some operation in the initially prepared dependent qubit. Maybe now they to try to meet and interact in some way, and now they may become correlated. And it is possible that instead of being product like this, they could be some other more complex linear combination of different product states. And that's what we are going to look at. Questions so far? So vectors, in mathematics, vectors of this form are called decomposable. So this is the word that we use for this kind of vector in the product. And in terms of the physics of things, this means that these states can be prepared locally, independently. So this is the state of the first qubit. This is the state of the second qubit independent of each other, no correlation. And it's also possible to prove that local measurements, we are going to define exactly what local measurement is in a minute, but it means that we are acting individually in each of the qubits. Local measurement is independent of those, and the final state of one qubit is not affected or is not correlated. Affected is a really bad word. I don't know why I wrote it. Let me erase this now. Because it's completely wrong. It's not about affecting or changing information. It's about correlation. The final state of one qubit is not correlated with measurements performed in the order. Okay? All about correlation. That is in quantum system, especially to quantum bits, it's not always the case that the states can be written in this form. So there are states that are not decomposable. So let's do that. Question so far. And what we have when we have a decomposable vector. So the vector has like this. And here as I said, I'm focusing on two qubits. So I'll imagine that the is at this state. And use that's it. And W is also at this state, whatever. So when I do the product with the of plus one, plus one. And as I said in the beginning of the class, one of the main properties of the tensor product is linearity. That's how it was defined. So now we use linearity here to extend the tensor product. So this is going to be equal tensor zero plus a zero tensor one plus b one tensor zero plus b one tensor one. So just to make a notation a bit easier, we write AC 0 plus A 0 1 plus AC 1 0 plus BB 1 1. Okay? So whenever I have a decomposable vector like this, it is written in the standard basis of C form as this linear combination. Okay? Is it clear for everyone what I just did? Okay. So now the exercise is to show that this vector cannot be written this way. So let's check that. So the vector that we have is psi minus, which is 1 over square root of 2, 0, 1, minus 1, 0. And if we want to write this as we answer that, as we just computed, we will need to choose B and W in such a way that AC have to be equal to 0 because there is no 0 component here. AB needs to be equal to 1 over square root of 2. BC needs to be equal to minus 1 over square root of 2. And BD needs to be equal to 0 as well. Okay? So let's see what the equality to this equation here implies. So this one implies that A is equal to 0 or C is equal to 0. Okay? But if A equals 0, AB would be equal to 0, which is not possible because AB is 1 over square root of 2. If C is equal to 0, then we would be this to be equal to 0, which is also impossible because this is equal to minus 1 over square root of 2. So this is a contradiction, which means it is not possible to choose and value such that sign minus is equal to the things for that. So this is not possible. Okay, so this proves for us that there are vectors inside the space of two qubits that are not independent generations of one state for the qubit 1 and one state for qubit 2. Okay? These states are very special in quantum information and they require some interaction between the qubits. I cannot prepare these locally, which means that I cannot prepare these with each lab acting exclusively on its qubit. Okay? Question? We are not going into the details of it here, but if you study the set of product states, you can see what is the dimension of the set inside the set of all states of qubits, of two qubits, and you will see that is the minority of the state. So it's much easier that the state is not a decomposable vector. Okay? Question? Okay, so this word decomposable is what we use in physics. So in mathematics, we use decomposable, not decomposable. In physics, we use this product state, and they state they are not products represented by vectors that are not decomposable. They are said to be entangled. So this is the mathematical definition of entanglement, that the vector is not decomposable. So this means that this side minus and one of the most important ones. These guys going to appear everywhere during our course. Okay. Okay. So basically, what this means, okay, this state cannot be prepared locally. What I mean by locally, each part acting There needs to be some type of physical interaction between the qubits, even if it's not direct. For example, two atoms and they have they interact with light. Okay, so light intermediated the interaction between the two atoms. But there needs to be an interaction. They are correlated in some way. Okay, cannot be prepared locally. Local measurement in the sense that each part acting on its qubit to measure it. These measurements can exhibit correlations, as we're going to see in a minute. And the qubit's final state can also exhibit correlations. Okay, so it's really important here. Of course, we are all you already study a lot of quantum physics, so you're not going to fall for these things that you can see in journals like television or that. Entanglement means that what you do in one qubit instantaneously affects what happens with the other. It's not true. That's definitely not true. It's all about correlation. Okay? Correlations also exist in classical systems, and it doesn't mean that you have instantaneous communication. So imagine a very simple example. I get a coin and I split it in half. One half will be tail and the other one will be head. I put these different coins, these different sides of one coin into different envelopes, and I send one to you and I keep the other. If you open your envelope when you receive it, you will see what is the half of the coin you have in your side, in your envelope, and you will automatically know what is inside my envelope. If you have tails, it means I have heads. If you have heads, it means I have tails. It doesn't mean that I'm communicating or you are communicating instantaneously. You know that our halves of the coin are correlated because they are halves of the same coin. So whenever you learn what is your half, you know what is my half. There's no instantaneous communication here. Of course, in quantum physics, the kind of correlation I'm talking about is different. It's more powerful in some sense. I would be cautious to make this kind of claim because what doesn't need to be more powerful. It is different because the mathematics of quantum physics is different. The kind of correlation that it can exhibit is different as well. And we need a different kind of mathematics to describe it. But it's not about instantaneous communication. So every time you see claims of, oh, you measure one qubit and the other one is affected instantaneously, it is false. Okay? It's all about correlation. Outcomes are correlated, final states are correlated. These correlations require the mathematics of quantum physics to be explained. They cannot be explained by simple examples such as this of the coin. It's much simpler, but it's all about correlation. There's nothing of instantaneous communication. Okay. Okay. Another important consequence of the entangled state is the following. So if you have a product state, now what we have been doing so far in this class, we start with two individual qubits and we want to describe the joint system. Now imagine that you want to do the opposite. You have a joint system, but you don't actually care about qubit 2, you just want to describe qubit 1. Or the opposite, you don't care about qubit 1, you just want to describe qubit 2. So from your point of view, one of the qubits is not interesting. I would like to have only the state of my qubit, like for example, qubit 1. I will just throw away qubit 2, just look at qubit 1. If your state is decomposable, if it's the product state, it's really easy. If you want to describe qubit 1, you just forget about W and just use V. And the same for the other qubit. If you just want to describe qubit 2, just forget about V, about qubit 1, and use W to describe your system. But what happens if the state of the system is entangled? In this case, it's not possible to associate a state vector to your subsystem, to qubit 1 or to qubit 2 individually. This is really important. So the state of each of the individual qubits cannot be associated with a vector in its state space. So this is one of the reasons why we will have to change our definition of state, which we'll do sometime next week or the other. Okay. So this notion of state that we are using here is going to change. So it's the first notion, then we're going to generalize it because there are situations in which we cannot describe our quantum system using this kind of mathematical object. Okay? Okay, so there is a really important set of entangled states or sign minus that we worked before here, but we have some brothers. They're called the Bell states. You're going to learn why they call Bell states and why they are important. They are going to show up all course. And you can easily prove doing something similar to what I did with pi minus, that they are all entangled. And later in the course, we will see there are like grades of entanglement. You can more or less entangled. And there are many ways of defining this graduation of entangled. And these are the maximum entangled states of two qubits. Okay? We are going to go into that later. This is not important for now. The only thing that is important is that you understand that these are entangled. Okay?